Okay, well, welcome to the final episode of Ergotic Theory, Geometry and Dynamics. I just want to start by saying that for everyone, I know this semester has been a bit of an experiment, and I really appreciate everyone's participation in this class and their persistence in coming right up to this final day. It's been a lot of fun for me to work on presenting these results. It's been fun meeting people in office hours, and I hope those of you who did the homework also enjoyed the problems, because they're, I think, a big part of the course, and there's a lot of problems left if you want to do more after the course is over. So today I want to discuss property T, which we defined and discussed a bit last time. Its basic properties, and what we're going to prove is that property T holds for SLNR, and then ultimately that it holds also for lattices in a Lie group once it holds for the Lie group itself. And so let me just state the theorem that will give most of the details of SLNR and SLNZ have property T. And in this case, since this is at least for this group, it's this very strong form of non-immutability. But then we'll see this requires that n be greater than or equal to 3. It does not hold for SL2. And so there's an interesting phase transition that holds as these groups get larger and larger rank, and particularly this is a rank 2 or higher phenomena, so-called higher rank phenomena. Okay, so as I mentioned last time, there's going to be a couple of pillars of knowledge that we've developed so far, which will be very helpful in doing the proof. And I think one of the nice aspects of the proof is it brings together many elements of the discussion so far. So the first pillar has to do with unitary representations of P. So I'm going to do the case n equals 3 just for concreteness. So let's let P be R2, and then its dual group is also R2. It's really the Fourier transform space for the original space P. And then let's have rho mapping P into the unitary operators on some Hilbert space H be a unitary representation. And then and let's let F be an element of this Hilbert space, say with the norm of F equal to 1. Okay, now here's the way you should think about your Hilbert space H. It's spread out over your space P hat. And P hat is really the space of characters of the group P. And the irreducible representations of P are one-dimensional. And so you imagine that you decompose H into subspaces where it acts by a given character. Now, unfortunately, that decomposition may be continuous. But if you have a set of, say, a Borel set or a measurable set contained in the dual space, you can look at the part of the Hilbert space where the group P acts by these characters. So to every Borel set in the dual space, we get a projection pi a from H into itself. And the image of this projection is the part of the representation where the group P acts by characters in this Borel set A. So as before I mentioned, you can think of this as there's sort of a Hilbert space bundle with a fiber C over each point here, and then the Hilbert space itself consists of sections of this bundle. So if you have a section, you can, which is what an element F is like, you can restrict it to one of these Borel sets, and that gives you a piece. of this L2 function. So the main point is that from F in H, we get a measure on P hat. And this measure is defined in a very simple way. The measure associated to F of a Borel set A is just the norm of the projection of F to that Borel set squared. So F has, I started out with F having norm 1, and it has, so this is, of course, less than or equal to 1. And you can easily verify using properties of projections that it satisfies the axioms to be a probability measure on the dual space. Okay, so this is part of the spectral theory. And for example, if P were just acting on R2 by translation, then this F here would really be the Fourier transform of F as a function on P hat. And then the measure would be just the absolute value of F hat squared. So you can think of mu F as being like the absolute value of the Fourier transform of F squared, dc, which is something you can integrate over any subspace of P hat, and you get a number between 0 and 1. Okay, so that's a beautiful idea. Points in the Hilbert space give rise to measures on the dual group. The second point is now going to bring the group SL3R into play. So I mentioned P here as R2. I'm going to be interested in actually thinking about the group SL2R semi-direct product P, or semi-direct product R2. And you can think of this as the set of transformations of the form X goes to AX plus P acting on R2. So you act by translation by a vector in P, and then you're also allowed to make a linear change of coordinates of determinant 1. So it's sort of an affine, a group of affine transformations of R2, and this group sits inside of SL3R. And in particular, P sits inside of SL3R. So the way it looks is we put 1 here, we put 0 here, and then the vectors in P are column vectors in the last column of this matrix, and then here we put a matrix in SL2R. So that gives us a subgroup which is isomorphic to this semi-direct product or affine group. And now the thing I want to highlight here was, so here the thing I wanted to highlight was that when we have a point in our Hilbert space, we get a measure on P hat. And here I want to highlight the fact that if this is a consequence of the Hal Mohr Theorem, the theorem that if P has a fixed vector, in other words, if we have a representation of, suppose we have a representation of this whole group, and then if P has a fixed vector, meaning that the subspace which is fixed by all the elements in P is non-trivial, then this implies that SL3R has a fixed vector. So once you get a vector fixed by a small subgroup, you get a vector fixed by the whole group. And this is a consequence of the Hal Mohr Theorem, which we usually would describe in a sort of opposite way. So first, not having a fixed vector is like being ergodic. So the way we would usually say this is that if SL3 acts ergodically, then it's also mixing. And so every one of its non-compact subgroups also acts ergodically. So ergodicity of this big group implies ergodicity of its non-compact subgroups like P. And so if this has no fixed vector, then neither does this. Okay, so for the purposes of this proof, it's nice to think about this in sort of the contrapositive form. Okay, so if we're trying to show SL3R as a fixed vector, then it's enough to show P as a fixed vector. And the final statement is one which is very elementary, and yet it's the whole engine of the proof. And this is one thing I really find remarkable about this insight of Kazhdan that this property holds, because it comes down to something very simple, which is that there is no SL2R invariant probability measure on the circle, where we think of this as RP1. Or if you like, we think of it as the boundary of a hyperbolic plane, the way we have geometrically for some time now. Okay, now why is there no invariant measure on SL2R invariant measure on the circle? So this is something I hope that your feeling about SL2R on the circle now is enough that this is intuitively obvious, but let's give a formal proof. So let mu be such a measure, an invariant probability measure on the circle. Then the first thing to notice is that mu has no atoms. That is, it can't assign positive mass to one point. It has to be diffuse. Why can't an invariant measure have atoms?
The orbit is dense?
Yeah, I mean, in fact, it's not just that the orbit is dense. SL2R acts transitively on S1. S1 is a homogeneous space for SL2R. So if you have an atom at this one point, say it has mass a tenth, then at any image of that point under SL2R, you would also have to have mass a tenth. That means every point on the circle has mass a tenth. Well, probability measure is not going to have that property because the sum of those things would be infinite. So it has no atoms because SL2R acts transitively. That would be crazy. As Tina says, even if we just knew that every orbit, if we knew every orbit of the group were infinite, this would already be a contradiction because you would have infinitely many points, each of which has mass a tenth. On the other hand, so let's suppose it has no atoms. A particular subset of the circle is the real numbers. And a particular subgroup of SL2R is translation by 1. So we can let T of x be x plus 1 acting on the real line. Now, if we had a translation invariant measure, an SL2R invariant measure on the circle, it would restrict to give a translation invariant measure on the real line. I claim there is no probability measure on the real line invariant under translation by 1. Why not? Somebody else.
It would have to be infinite again.
Yeah, why, Catherine?
Well, if you had any mass somewhere, then you could just translate it by 1 and take that mass to infinity.
Exactly. So as soon as you cut the interval, the real line, into countably many segments, each of length 1, as soon as one of these has positive mass, say a tenth, then the next one has to have positive mass, and the next one has to have positive mass. And again, that contradicts the fact that this is a probability measure. So we can conclude that there's no T invariant measure of finite mass. Or put differently, any finite T invariant measure on R must be 0. but R occupies all of the circle except for one point. So if you had a translation invariant measure on the circle, it would have to vanish outside the point corresponding to infinity, but then its mass would have to be concentrated at infinity, which implies it would have an atom, and that's a contradiction. Okay, so there is no SL2R invariant measure on the circle. The measure theoretic action here is very interesting, but it's very wild, and it doesn't fit into the kind of ergodic theory we've been discussing. There is no SL2R invariant measure. Okay, so now what we're going to do is take these three facts and put them together to prove the first part of this famous statement of Kochtland's. And the proof is really slick, I find. So here we go. So let's prove this. I'll just prove this. SL3R has property T. Okay, so we suppose not. So what does it mean to not have property T? It means that there exists a representation of SL3R into the unitary group of some Hilbert space H with almost invariant vectors but no invariant vectors. Okay. And what we're going to do is we're going to show that if this happened, we could use it to construct an SL2R invariant measure on the circle, which we know doesn't exist. So that's going to be the contradiction. So all we have to do is get from the existence of this representation to the existence of such a measure. So here we go. So it has almost invariant vectors. Okay. So so the fact that it has no invariant vectors, well, okay, so let's start like this. Let K contained in SL2R, by which I mean this SL2R here, sitting inside of SL3R, be compact and generate SL2R. So it could just be a compact neighborhood of the identity. So then, for any compact set, there exist almost invariant vectors. So there exists Fn in our Hilbert space, say with the norm equal to 1, such that the variation of Fn over K is as small as we want, is tending to 0. And I'll remind you what this quantity measures is the soup of the norm of Kf minus F over K and K. So when we move these vectors, we apply an element of K to these vectors, they don't move very much in the Hilbert space. They're unit norm vectors, and they just jiggle back and forth a little bit. Of course, their length is preserved because the representation is unitary. Okay, now here comes the brilliant step. We look at the measures mu n obtained by applying the spectral theorem to P. So remember, these are also, this representation of SL2R also gives us a representation of the subgroup P. And so we can apply the spectral theorem, that is, we can take these Fs and we can decompose them over P hat. We can look at their Fourier transforms with respect to P hat. So these measures are measures on P hat. These measures mu n are on P hat. So they're on this dual vector space. Now, what can we say about these measures? Well, we haven't yet used the fact that there are no invariant vectors. But now we're going to use the Hal Mohr Theorem. The Hal Mohr Theorem says, since we have no invariant vectors for SL3R, we have no invariant vectors for P. So these vectors are not invariant. There is no invariant vector for the action of P on this Hilbert space. And that means the trivial representation does not occur when you decompose this representation over P. And that just means these measures have no mass at 0. 0 is the trivial character, and it corresponds to the trivial representation. So mu n do not have an atom at 0. So these mu n's applied to the point 0, the measure they attach to this is 0. There's the origin in our vector space P hat. These measures don't give you any mass at the origin. Okay, don't blink, because we're almost done. Okay, so now let me draw the picture more realistically. Here's P hat. It's R2. Here's the origin. And then we have these measures mu n. Now, what I'd like to do is take a limit of these measures. But the problem is that P hat, being R2, it's not compact. The measure might just drift off to infinity, and the mass disappears. The limit is 0. So what I'm going to do is take P hat minus the origin, which is okay, because their measure puts no mass at the origin, and I'm going to project that to RP1. In other words, to the circle. So just draw a circle at infinity for this space, and then project these measures out along the lines through the origin. That's what pi is. Okay, so from these measures on P hat, I get measures on the circle. And I'm using here, and the fact that these are probability measures uses the fact that there's no atom at the origin. So we let mu n be pi lower star of mu n. This is a measure on, a probability measure on the unit circle. And now we're done. Why are we done? You see, the variation of Fn over K is tending to 0. Well, the group SL2R acts on the vector space P. It also acts on its dual. P hat is just the dual space of P. It's the dual vector space. So A acts by A transpose on the space P hat. So SL2R is also acting here. And inside of this, we have this compact group K, and it's moving these vectors less and less. And so it's moving these measures less and less. And therefore, it's moving these measures less and less, because this projection map respects the action of SL2R on its domain and range. On the other hand, this is a sequence of probability measures on a compact space. So we can pass to a subsequence and obtain a limiting measure. So pass to a limit, let's call it omega, the limit of mu n sub k. And then, since the variation of Fn tends to 0, this limiting measure is actually K invariant. So then omega is K invariant. But K generates SL2R. And so this implies that it's SL2R invariant. And we just saw that's a contradiction. Okay. So that's impossible, and therefore we have property T. In other words, if we didn't have property T, the almost invariant vectors would give rise in the limit to an SL2R invariant measure on the circle. Great. Now, so this is already quite striking. And as I mentioned, this holds up not just for SLNR. The key point is that what we used here was that we could fit inside of our group a copy of something like SLN minus 1 cross RN minus 1. And there's a lot of groups, and in fact, all we needed to get inside was a copy of SL2 cross R2. And then we could leverage this argument. So there's basic theorems in the structure theory of Lie groups that say any semi-simple group, as long as it has a big enough diagonal subgroup, contains copies of SL2R with this semi-direct product. So in fact, this theorem holds for semi-simple groups of what's called real rank bigger than 1. But for our purposes, the thing to keep in mind, just as something you'll remember, is that this is true for every n greater than or equal to 3 by essentially the same proof. Okay. But now suppose we were interested in constructing expanders, or we just like discrete groups, or we wonder if we can make some nice finitely generated groups that have property T. Because we haven't seen any of those. The only groups we've seen with property T so far have been finite groups. So the next theorem is that SL and Z has property T. And it's well known that SL and Z is a lattice in SLNR, just as we know very well for n equals 2. So to prove this, it suffices to prove the following theorem, which is that if G is a Lie group and gamma contained in G is a lattice, and then if G has property T, then so does gamma. Okay, so let's think about what this means. It means we have to take a representation of gamma that has almost invariant vectors and prove it has invariant vectors. So to do that, to leverage the fact that gamma is a subgroup of G, we need some way to go back and forth between representations of gamma and G. So I'll show you how to do that in the course of the proof. It's a very important and general construction called the idea of an induced representation. Just raise your hand if you've ever heard the words induced representation before. Thank you for raising your physical hands. Okay, great. So this will be a review. So what we do is the following. We say, suppose we have a representation rho from gamma into UH. And let's not put any hypothesis on it for the moment. Then we get a representation rho tilde from G into a new Hilbert space H tilde as follows. And I'm going to tell you two ways to do it. There's a sort of a lowbrow version and a highbrow version. The lowbrow or brass tacks version is this. You let H tilde be the set of maps F from G into H. These, of course, should be measurable or Borel. Anyway, reasonable maps from F from your Lie group into the Hilbert space H where gamma is acting, with the property that if you apply an element of this lattice to your function f, the vector you get changes, it's twisted by the action of the lattice on this Hilbert space H. That's it. That's the definition of H tilde. Now, of course, you want to have a norm on this space. And the norm can be described as follows. We let D contained in G be a fundamental domain for the action of gamma. So in other words, we want gamma dot D to equal G, and these sets should all be disjoint. D might be a polyhedron, it might even be a Borel set in principle. And then we define the norm of F in this Hilbert space H tilde squared to be the integral over this fundamental domain of the norm of the value of F at each point. Let's call this little G squared. That's with respect to the original Hilbert space where gamma acts, and then with respect to Haar measure on G. Okay, so that's one version of what this induced representation is. And there's a slightly different version, just if you want to have another way to think about it, which is quite natural. You see the map from G down to gamma mod G is a covering map. And so whenever we have a representation of the deck group on a vector space, we get a bundle, a flat bundle over the quotient space. So this is the first presentation. The second presentation is you build a space which you might describe as G cross H over gamma, which is some Hilbert space bundle, call it curly H, and this sits over G mod gamma. And then these F can be interpreted as sections of this bundle. The fibers of the bundle are Hilbert spaces, and then the norm can then just be described as the norm of F squared H tilde is just the integral now over gamma mod G of the norm of F at each point squared in the particular fiber in which it lies. Okay, so those are two different ways of thinking about this kind of induced representation. One reason this version is often useful is sometimes this G mod gamma or G mod K mod gamma, this is close to being something like an algebraic variety. Maybe this vector space is finite dimensional. Then you get an honest algebraic vector bundle over some reasonable space. Whereas here, we've kind of fractured the picture by choosing a fundamental domain. However, that's very convenient for the following reason. What I'd like to do, now that I have this representation of big G, is I'd like to relate it to this representation of gamma. And for that purpose, I need to take elements in the representation of gamma and put them into the representation of G. And that can be done as follows. So this being a cultural aside, I'll stick with version 1 just for concreteness. So now we have a map from the Hilbert space H into the Hilbert space H tilde. And we have gamma acting on both spaces. Gamma acts here via our original representation rho, and it acts here via our representation rho tilde, because after all, it's a subgroup of G. And how do we make this map? Well, it's very simple. I want to take an element of this Hilbert space here and turn it into a function on G. But G is already tiled by these fundamental domains, D, gamma 1D, gamma 2D, etc. So what we do is we say phi of little f is equal to big F, where F restricted to the original fundamental domain D is just equal to the constant vector F, little f in H. So we take F to be a constant on this fundamental domain. Of course, it's a constant as a map into H, and we just take it to be the value that we started with in H. And then what should we set it equal to on the other translates of the domain? Well, there's only one choice, given the fact that we need this law to hold. So F restricted to gamma D is equal to rho gamma dot F. And then that gives us an element in this Hilbert space. And by the way, if we normalize Haar measure so that the volume of gamma mod G is equal to 1, which we can always do since this is a lattice, then this map will be in isometry. So it actually gives us a lifting of this representation of gamma to a sub-representation of H tilde. Okay, so this representation rho tilde is often denoted by the following way. It's the induced representation from gamma to G of rho. Okay. So now we're almost done. So maybe we should just finish by sketching what the proof is going to be. Sorry, the statement has to disappear, but we can remember that. We're trying to show gamma has property T. So the remainder of the proof works like this. We suppose that rho, which is our representation of gamma, has almost invariant vectors. We call them Fn. Then we use this to produce almost invariant vectors for G with respect to this induced representation. But then, since G has T, this implies G has an invariant vector. Okay, now what does it mean for G to have an invariant vector? It means that when we take this function f here and we apply an element of G to x, it doesn't change the value of f. But G acts transitively on G. So an invariant vector here is simply a vector such that capital F is constant. If we have an invariant vector, this implies F is constant. So say F of G is equal to some little f for all G. But on the other hand, capital F satisfies this condition. So in particular, little f is equal to f of gamma, which then has to be gamma times f of the identity, which is little f, which is gamma times little f. And so f is, this constant value is fixed by every element in our group gamma, which implies gamma has fixed vectors. Okay. So we're almost done, and all we have to do really is this step. We have to take an almost invariant vector for gamma and use it to produce an almost invariant vector for G. And it's pretty clear that what you want to do is use this lifting map phi. In fact, why not just take phi and apply it to these vectors Fn? And in fact, that works, but there's a small nuance in the proof I want to draw your attention to. So let's think about what we have to prove to show A implies B. So the trick here is that to prove something is almost invariant for G, we have to prove that it's almost invariant under a compact subset of the group G. And then we have to somehow relate that compact subset of G to a compact subset of gamma, which means just a finite subset of gamma. So we let K contained in G be compact. And if you like, we can assume it generates G. And then we want to find vectors that are almost invariant under this. Now what we're going to do is we're going to make those vectors we're going to choose those vectors by specifying their values on the translates of these fundamental domains. And since K is compact, when you take K and you apply it to D, you get a set of finite measure. And what I'd like to write is that this set of finite measure is the disjoint union of finitely many tiles. Because after all, these translates of D by elements of gamma form a partition of the big group G. And in fact, if D were compact, this would be true. I could find a finite tiling with this property. The problem is that these domains D here might have not be compact. We saw this problem also in the case of SL2R, and it might be that when we apply K to D, we get some little region like this, which intersects infinitely many copies of D. But it doesn't matter, because you see, this set has finite measure, and it's equal to the union of, sorry, it's not equal to this, it's contained in this. It's covered by all of the tiles. Well, since it has finite measure, it's the amount that's left over after you've covered by many tiles has measure going to 0. So we can choose finitely many tiles such that K dot D is contained in this union a set of measure epsilon. So this is almost true. Now, here's what's really useful. At this point, we've drawn our attention down to just finitely many elements of gamma, these gamma i's that describe these finitely many tiles. So we let S be that set gamma 1 up to gamma n. That is a compact subset of gamma. And gamma has almost invariant vectors. So now we can choose F and H norm 1 such that the variation over this finite set of F is less than epsilon. And now we let capital F and H tilde be given by phi applied to little f. So we just lift it to the values on the corresponding tiles. And now what we notice is that if you pick a point, so then I claim that then F is almost invariant. So if we pick a point X in D, then Kx is in K dot D. And as provided we neglect this set of small measure epsilon, that implies Kx is in gamma I dot D for some gamma. But then F of Kx is just equal to, by the definition of phi, a row of gamma I applied to little f. And this vector is within distance epsilon of the original vector f, because of the fact that f is almost invariant under gamma. And so putting those two things together, so this is very close to being f. And so putting those two things together, we get that the variation over K of big F is less than 2 epsilon. 1 epsilon coming from this, and the other epsilon coming from this neglected set of positive measure. Okay, so almost invariant sets for the lattice give rise, vectors for the lattice give rise to almost invariant vectors for the big group, and then property T allows us to conclude they're invariant vectors, and then that descends back down to gamma. Okay. So this is really the first example that was ever given of a discrete infinite group with property T. Okay, and now what might you want to use these for? Well, there's many interesting things one can do with groups with property T, but the one application that I had in the back of my mind, which was motivation also for study of eigenvalues of the Laplacian, was to expanding graphs. So now that we have some nice groups with property T, let's use them to produce some expanding graphs. And this is very easy. So as a corollary of this, we have the following: fix a finite generating set S for SL3Z, and let Gn be the Cayley graph of SL3Z mod n using that generating set or its image under the reduction mod n map. These form a sequence of expanders. And in fact, the right statement here would be, instead of SL3Z, we could say any infinite group with property T, and then instead of SL, let me call that group G, instead of SL3Z mod n, we could say any sequence of quotient groups Gi, G mod Hi, with the cardinality of Gi going to infinity. And S would again be a finite generating set for this group, and then we get an infinite sequence of expanders. Okay, and the proof of this is very familiar by now. Let me just say how it works. So the proof is, and it's kind of cool, we let SL3Z act on L2 0 of SL3 Z mod n. So this is if we call this group G, this is of course the quotient of G by a normal subgroup. In fact, it's by what's usually called gamma of n. Sorry, let me just call it H of n. Anyway, this is a finite homogeneous space for this group. So of course it acts by left multiplication here. And this group has property T. And so this representation has property T. And so what we find is that for any vector here that we pick, say with norm 1, that is any function on this finite group, the finite generators of this group move that function a definite amount. So var s of f is greater than or equal to some constant lambda greater than 0, which is independent of this quotient group. In fact, it depends only on SL3Z. This is the amazing thing about property T, is it gives you a constant which only depends on the group, and then it works for every single unitary representation in the world, provided there are no invariant vectors. And that's why I'm restricted to the functions of mean 0. So every function gets moved a definite amount by these generators. But now, if we think of this in terms of the graph, Gn, as usual, if we have a partition of this graph, or if we have a subspace of it with less than half the size, we can make a function. Let's say we have a partition like this. Then we have these edges, which come from the generators S. And we make a function such that f restricted to A is, say, the cardinality of B, f restricted to B is minus the cardinality of A, so that the integral of f is equal to 0. And it's not quite norm 1 yet, but you can see that for this to vary a definite amount, when you apply the elements of S to it, it means that when you start in A, and you hit an element of A with something in S, it usually moves outside of A. If it stays in A, the value of the function doesn't change. So most of the time, points in A are pushed into B. And what that means is that the size of the boundary of A must be comparable to the size of A itself. So the size of the boundary of A over the size of A is bigger than some lambda prime greater than 0, which doesn't depend on anything but the original group. And therefore, we have a sequence of expanders. Okay. So that's a brief introduction to what happens in higher rank Lie groups. We get a very strong form of non-immutability called property T, and it passes to their discrete subgroups. And moreover, this property T can be seen and ratified by these finite combinatorial objects, namely these expanding graphs. Okay, so that's where I have to end this long story, but I want to spend a few minutes looking back and thinking about what the story actually was, and maybe just jog your memory a little bit about where we've started and where we've ended. This was not a story in which Captain Ahab pursued the whale and then we finally captured the whale or were destroyed. This has been rather a sort of a panorama of ergodic theory, but it has a certain narrative to it. So let me try to say now that we're at the end what that narrative was. So when we started studying ergodic theory, we had two main examples. So who can remember what the first example was of an ergodic transformation that we studied?
Irrational rotation.
Yes, the irrational rotation of the circle. So our general setting was we had X, we had a transformation T, and we had a probability measure mu that was preserved. And our first example was the circle with an irrational rotation. And our second example was the torus with a hyperbolic automorphism. So this was an area preserving map coming from an element in SLTZ, and we chose this to be hyperbolic. So we have two examples of measure preserving dynamical systems. And the first thing we proved that these were both ergodic. And then we saw that the ergodic property implies a lot of strong additional properties, especially via the ergodic theorems. It implies that when you sum functions along orbits, that they tend to the average of functions at almost every point, or in L2. And the L2 proof was easy. That it was von Neumann's theorem. The AE proof was a little bit harder. That's the Birkhoff-Hünchen pointwise ergodic theorem. So in retrospect, though, we can think about this in the following way. You have a function on a space, and you'd like to determine its average. Like you want to do polling in a certain community in Massachusetts. So one way you might do it is by choosing a bunch of individuals at random and calling them up and finding their voting preferences. But you could also poll using a deterministic dynamical system. So you take, I don't know, their phone number and you apply an irrational rotation to it over and over again. And you sample these points, assuming every number corresponds to an individual. And that sequence behaves like a random sample, at least for almost every choice of starting point. So the ergodic theorem, in retrospect, says that deterministic but ergodic dynamical systems behave as if their orbits are random samples of the space in which they lie. However, that's only the tip of the iceberg, because there's lots of other properties that distinguish these kinds of dynamical systems. And in particular, what we saw here was this is irrational, but it's not mixing. There's no stirring up of points. When you start with an interval and you rotate, no matter how many times you rotate, it remains an interval. It doesn't spread out over the space. Whereas here, we proved that this transformation was mixing. That's one approach to seeing that these two dynamical systems are very different. Another approach, which was really the key to our future developments, was that we studied both of these properties by using the associated unitary representation of the group. Now, the group didn't play a very big role here because the group was just the group generated by T, which is Z. So we usually didn't even have a name for this group. But indeed, in all of this study, we were really considering representations of G into L2 of X, into the unitary transformations on L2 of X. And so we started by adopting this unitary perspective. And if we got rid of the constants, then ergodicity was equivalent to no fixed vectors, et cetera, et cetera. And mixing had to do with the inner products between G, F, and F, showing this tends to 0 as G goes to infinity is exactly mixing. So what we began to see is that ergodic theory can be approached via the study of unitary representations of groups. And then, of course, there were other invariants which emerged, like the spectrum of an operator. That's essentially classifying which irreducible representations of Z occur. So in fact, in the background of this was the fact that G hat is equal to the circle. And then each of these representations gave rise to a spectral measure on G hat. For the irrational rotation, it was a purely atomic measure. And here it was Lebesgue measure of infinite multiplicity. So very different spectral measures. Okay. So there's two other highlights I want to remind you of at this stage in our discussion. One is that this not mixing transformation, which looks like it's not very good from the point of view of ergodic theory, this looks much more chaotic, had one very good property which was not enjoyed by this guy. Namely, this is uniquely ergodic. That's a topological property. There's only one invariant measure on the circle. And that implies orbits are always equidistributed and so on, many things that didn't happen here. It also forces the absence of periodic points. So there are no periodic points here. There's tons of periodic points for this action on the torus. The other thing I want to remind you is that there are many proofs of mixing here. You can give one using Fourier series. That's the sort of harmonic analysis or unitary representation perspective. But there was a very conceptual proof, which I mentioned, I hope, if you remember only one thing from the course, it's this thing, and it's the Hopf argument. So the Hopf argument for ergodicity of TA was the following. We look on our torus, and we have a pair of foliations, one of which is expanded by T going forward and one of which is expanded by T going backwards. And the ergodic theorem assures us that if we take the averages over the forward iterates of F, sorry, let me call this, I didn't have a notation for my transformation. Let me throw that in. If we take the ergodic averages for TA of F, that's the same as taking the ergodic averages for TA inverse of F. Because in both cases, we just get the projection of F to the invariant functions. But the ergodic averages going forward in time were almost obviously only dependent on which leaf of the white foliation you started on. So the average for this point X and the average for this point Y have to be the same. But the averages going backwards by the same argument have to be the same along the red leaves of the foliations. So the average also has to be the same here at Z. Well, therefore, the average is the same everywhere, and therefore the transformation is ergodic. So that's the famous Hopf argument. And the idea again is that if you have a dynamical system where the past does not allow you to predict the future very well, and vice versa, so this is the past and this is the future, then the ergodic averages will not depend on the past, but they'll also not depend on the future by the Hopf theorem, and therefore they won't depend on anything. Okay. Now, why do I bring up the Hopf argument? It's partly because it's so robust that it doesn't require harmonic analysis, but it's also that our next topic was the study of hyperbolic surfaces. And more generally, hyperbolic geometry. And here we really did change the group. We changed the group to SL2R. Although within this group, we studied especially the geodesic flow and the horocycle flow coming from these two one-parameter subgroups. And of course, there was also the compact group of rotations was important. And one of the key things I hope became clear in our study of hyperbolic surfaces, which is in hyperbolic geometry, which is that this is not just the study of the hyperbolic plane. The hyperbolic plane is important, but it's just one of the homogeneous spaces for G. And there's also G mod n, which is the light cone, and there's also G mod A, which is the one-sheeted hyperboloid of geodesics. And all of these different reflections, different geometries attached to SL2R play important roles in hyperbolic geometry. And they're all kind of united nicely in the Minkowski model, where you can see them all at once as the light cone, hyperbolic space, and the space of geodesics. Okay, and then in this setting, we return to the question of ergodicity, and now we don't have an abelian group anymore. We can't do kind of trivial Fourier analysis to prove anything, but we have more powerful tools like this Hopf argument. And so what we proved was that on G mod gamma, which is like the unit tangent bundle of a hyperbolic surface, we proved that geodesic and horocycle flows are mixing. And in fact, we proved that the whole action of G is mixing on L2 of this quotient space. Now, the proof we initially gave used the Hopf argument to prove that the geodesic flow was ergodic. Implied that this was ergodic. But then from then on, the proof was pretty general. It didn't use very much about hyperbolic geometry. And in fact, we later saw that once you know the geodesic flow is ergodic, everything is mixing. So this theorem is, in retrospect, an easy consequence of a special case of the Hal Mohr Theorem. So the Hal Mohr Theorem said that if SLNR acts ergodically on a space X, then it is mixing. And in fact, it doesn't even have to act ergodically on X. It just has to act unitarily on some Hilbert space H. And then ergodic theory means that the set of fixed vectors is trivial. And once you have that hypothesis, you get that it's mixing. So I want you to notice the transition that took place here. So at the beginning of the day, we had a transformation in a space, but the group Z was of little interest. But when we start to look at richer actions of groups, in particular actions not of one parameter abelian groups, but of simple Lie groups like S, L, N, R, as soon as n is greater than or equal to 2, we almost don't need to know anything about the action to get mixing. Mixing is a consequence of ergonicity plus the fact that this big group is acting. And remember that ergonicity, we have many methods to prove, such as the Hopf argument. So once we've done Hopf, the rest of our study of the dynamics of the geodesic and horocycle flows only depended on the group. It did not depend on the space. This holds for all unitary representations. And to illustrate the power of this, I proved rather quickly that, the action of SL2R on the cotangent space to the moduli space of Riemann surfaces is mixing. See the unit cotangent bundle to moduli space, and in particular, the so-called Teichmuller geodesic flow is mixing. So this is a much trickier kind of action to get one's hands on, and yet the proof that we have mixing is very fast and very formal once you know that something is ergodic. So as soon as you know the Teichmuller geodesic flow is ergodic, everything is mixing. It's because it all comes inside of this SL2R package. So that's illustrating the power of this single group. Okay. Now, what else did we prove in the case of Riemann surfaces? Well, one thing that was very significant and brings us back in the direction of the irrational rotation was this. If X is compact, then the horocycle flow is minimal and uniquely ergodic. So when you're starting to work with these unitary representations, you're never going to see anything about the behavior of individual orbits because they have measure 0. One orbit has measure 0. But in fact, extremely strong properties hold for the horocycle flow. You start drawing any horocycle on a compact Riemann surface, well, it can't be closed. And in fact, it's dense and uniformly distributed. So this was the theorem of Hedlund, that it's minimal, and the theorem of Furstenberg, that it is uniquely ergodic. Now, the proof of this involves some new techniques, which I just want to remind you of. So we studied the space of horocycles, G mod n, and the way this kind of proof worked was we leveraged the study of a double coset space, n mod G mod n. And this space, as we discussed at length, classifies pairs of geometric objects. Every double coset space classifies a pair of geometric objects. This one classifies the moduli space or the configuration space of pairs of horocycles. And it's not Hausdorff. And by exploiting the fact that it's not Hausdorff, we were able to prove that the horocycle flow is minimal. And we didn't complete the proof that it's uniquely ergodic, but it involves many similar ideas. By the way, the idea of double cosets also plays an important role in this theorem, because to study the behavior of a unitary representation, we study the function phi of g, which is GFF. And if F is A invariant, then G is a function on G mod A mod A. You can apply A to either side, and you don't change the value of this function. And so the method of double coset also played in to the theory of representation theory of simple Lie groups. So it's a very powerful technique, which is usually kind of hidden inside the proofs, and I tried to illuminate its use in these theorems. And the ultimate use of this theorem, this idea, is to get to Ratner's theorem. And what Radner's theorem showed us is that the key feature here is the fact that the horocycle flow comes from matrices that look like this, that have all ones on the diagonal. And Radner's theorem says that in the setting of homogeneous dynamics, any group that's generated by these so-called unipotent transformations has very rigid properties. So Radner's theorem allowed us to analyze the action of unipotent on gamma mod G. And especially it said that an orbit closure is usually equal to everything unless the point you started with is super special. It has some extraordinary property. And as an example of that extraordinary property, we sketched at least the proof of the Oppenheim conjecture, which said that if you have a quadratic form, it's of indefinite signature, and you look at its values on the integers, well, it tends to take on a dense set of values. And when does it not? Well, one way it might not is it's just an integer matrix. So when you apply it to integers, you get integers back, which can't possibly be dense. And Radner's theorem said that as long as the form has rank 3 or more, in fact, that's the only way the image can fail to be dense. So Radner's theorem is kind of the next step. This is sort of postmodern ergodic theory in the sense that it tells us stuff about the behavior of every single orbit rather than of almost every orbit, which is what the unitary theory is telling us. Okay, and then to make a long story short, what we've just seen is that as we progressed from Z and R to something like SL2R, and then to unipotent groups, we began to get stronger and stronger theories. But then there's yet another transition that occurs when you go to higher rank groups, and this is where we reach property T. And property T is some property of all unitary representations of the group. Just like the Hal Mohr theorem is about all unitary representations. And it's kind of, not only are all ergodic actions mixing, but they're somehow mixing at a very definite rate, which is provided by this uniform bound, and which is witnessed by the existence of these expander graphs. So the flow of ideas is that we started with space and a single transformation, and then as we carry the analysis further, and we're kind of following historical precedent here, the space became less and less important, and the group became more and more important. It turned out that many of the properties that people were proving about group actions only depended on the group and not very much on the action. And so that is the trajectory that I've tried to trace in these lectures. So I hope this has given you a sort of a panorama of many different things, ranging from hyperbolic geometry to spectral theory and representation theory. But I would say there's one topic which I didn't get a chance to address, unfortunately, just because we ran out of time, which is Moster rigidity. And let me just say a word about that. If we had time to analyze Moster rigidity, we would have taken this assertion that there is no invariant measure for the action of SL2R on the circle, and we would have analyzed the ergodic theory of groups acting on the circle anyway, even though there's no invariant measure. And in fact, we would more generally take a hyperbolic n manifold and analyze the action of its fundamental group on the sphere of dimension n-1. So that's a kind of audacious and different kind of ergodic theory because there's no invariant measure. And by leveraging that analysis, we would eventually prove something that's very discrete, namely that a hyperbolic 3 manifold is completely determined by its fundamental group as an abstract group. So if you want to have a sequel to the discussion so far, that would be a natural next chapter to read or learn somewhere else. Okay, thanks a lot for attending. Thank you for unmuting and clapping. Okay, so I'll hang around a bit if anyone wants to chat or has any questions. And for those of you who are doing the homework, remember that there will be office hours in section as usual. And even though there's no class on Tuesday, please hand it in by 12 o'clock next week.